All right, welcome to the video. We're going to talk about how to approximate the area under a curve using n number of rectangles, n being anything you'd like, 2, 3, 4, 5. We're going to develop the explicit formula to find these approximations, and then we're going to actually take the limit and let n approach infinity to find the exact area under that curve. So let's go have some fun. All right, so let's find the area under the curve of the function 5 minus x squared on the interval 0 to 2 using n right endpoint rectangles. Let's go. Let's first think about the width of each of these rectangles. Well, let's take 4, for instance. If I want 4 rectangles on the interval from 0 to 2, they have to be equal in width. Then I'm taking an interval of length 2 and dividing it by 4. And so the width of each of those rectangles or subintervals would be 1/2. Now, in general, the width of those rectangles, n being any number that I want, would just be the endpoint, the right endpoint minus the left endpoint, which will give me the length of that interval divided by the number of rectangles I want to use. Okay, so let's see what that looks like. There we go. Delta x is going to represent the width of each of my subintervals or my rectangles. If I take b minus a, b is the right endpoint, a is the left endpoint. So 2 minus 0 divided by the number of rectangles that I want. Right now we'll just say it's n. So 2 minus 0 is 2. 2 over n is my width of each of these rectangles that I'm going to use, or the length of these subintervals that I'm breaking up the 0 to 2 interval into. Now let's think about what it means to take right endpoint rectangles. Well, if I go to my sketch and I just say I want to use 2 rectangles, I would break this interval from 0 to 2 up in half. So each subinterval would be length 1. Okay, the right endpoint is going to be this endpoint. So this would represent the height of my first rectangle. The height of my second rectangle would be found by taking the right endpoint between 1 and 2. So each subinterval you want to take the right endpoint of. All right. In general, what are we doing? Well, let's just say x sub I, which is going to represent the right endpoint, is going to be found by taking the a value, or the beginning of the interval, and adding increments of the change in x, or adding increments of the width of each of these rectangles. Now, we just said in general the width of our rectangles using n rectangles is going to be 2 over n. And therefore, to get the first right endpoint, or the right endpoint of the first interval, I'm going to take the beginning of my interval, 0, and add an increment of the change in x, which is 2 over n. So in general, it's going to be a plus I change in x. So in our example, because our a value is 0, it's going to be 0 plus I times 2 over n, or 2 over ni. And just to keep things simple, we'll just keep that written as 2 over n I. Okay, so each of those increments, 2 over n I, is going to represent the right endpoint of each of my subintervals. The idea is, if we take, say, 2 rectangles like I have sketched in the picture, if I find the area of both of those 2 rectangles and add those areas together, that gives me an approximation of the area under the curve. If I use 3 rectangles, what will happen is the area of the 3 rectangles added together will be a little better of an approximation of the exact area under that curve. We want to increase the number of rectangles we use as much as possible so that the widths of each of those rectangles decrease so much that they'll be stacked on top of each other, and then we can finally find the exact area under this curve between 0 and 2. Okay, I hope that made a little bit of sense. If I'm using 2 rectangles, the width of each of these subintervals would be 1. The height would be found by taking the function value, in that case, the function value at 1, in this case, the function value at 2. The area of that first rectangle can be found by taking the width, which is 1, and multiplying it by the height, which can be found by the function value at 1, if I'm using the right endpoint with 2 rectangles. So we know the area of a rectangle is base times height, width times length, however you've learned it. It's the 2 dimensions multiplied together. So because I'm using the term width, I'm going to say width times height. Okay, so if my width of each of my rectangles is the change in x, and the height is found by taking the right endpoint of each of my subintervals, in general, we'll just say that's the function value at x sub I. That's the area of each of my rectangles. Now the idea is we're stacking these rectangles on top of each other and adding their areas together. So what does that look like? That looks like this. There we go. So what this notation means is we're going to take the sum of each of those areas of those rectangles between 1, I, the index being 1, all the way to n. So if I wanted to use 2 rectangles like you saw in the picture a second ago, my n value would be 2. If I wanted to use 4 rectangles, my n would be 4, and so on. But we want to keep it in general, and we just want to keep it as n right now. So let's plug those into our summation that we have, and we'll get this. There we go. So we have the sum from 1 to n of 2 over n times the function at each of those right endpoints, which is 2 over n times I, right? So if I is 1, we're looking at the first right endpoint. If I is 2, we're looking at the second. If I is 3, we're looking at the third, and so on. Okay, so remember your function is 5 minus x squared. There's our function. So remember what this notation means. This means to take the expression 2 over ni and substitute that in for x in your function. So when you do that, you'll get this. Let's scroll. All right, and I have in red the function at 2 over ni. So notice we're going to square 2 over ni. All right, when we square that, we'll get this. Okay, we have the summation from 1 to n of 2 over n. Remember, that's the width of each of my rectangles, times the function calculated at 2 over ni, which comes up to be 5 minus 4 over n squared times I squared. So there's a couple of algebraic ways to go about doing this. What I like to do, what I like to do is go ahead and distribute the 2 over n into my binomial. And when you do that, you'll get this. All right, so we're taking the sum of this now, okay? Remember, n is general right now. We don't know what n is going to be. We can use this explicit formula that we're going to develop and approximate the area and then eventually find the exact area. All right, so let's break this up into 2 summations. Okay, now we can use a couple of summation rules. This first summation, there's no I in here, so we can actually just pull this out. Okay, and then over here in the second summation, we can pull out the coefficient 8 over n to the third from the sum. All right, when we do that, we'll have 10 over n, and then the sum of I going from 1 to n of 1 minus 8 over n to the third times the sum from I going from 1 to n of I squared. And now you have to remember some explicit formulas in these summations. So let's scroll. If I take the sum from I starting at 1 going to n of just 1, then what that means is I'm going to take 1 and add it to itself n times. So what does that turn out to be? If you add 1 to itself n times, it doesn't matter what n is. Let's assume n is 4. Add 1 to itself 4 times and you get n times 1, which is just n. So this summation simplifies to just n, okay? So let's write that. So I got 10 over n times n minus 8 over n to the third. Now this summation, I hope you know the explicit formula for this summation, the sum of the squares from 1 to n, that is going to be written explicitly as n times n plus 1 times 2n plus 1 over 6. All right, and from here, it's just a whole bunch of algebra. All right, so algebraically, 10 over n times n is going to be just 10 minus, okay, I can go ahead and do some reducing here as well as go ahead and multiply the n plus 1 times 2n plus 1 times n. You would FOIL. The way I would do this is I would FOIL the n plus 1 times the 2n plus 1 and then distribute the n into that. But do a little bit of algebra and you should get this. Now the idea is you can take that -4 and distribute into that trinomial, 2n to the third plus 3n squared plus n. All that is divided by 3n to the third. Distribute that -4 and break this up into different fractions. And what will that look like? Now we have an explicit formula to approximate the area under the curve f of x is equal to 5 minus x squared from 0 to 2 using n rectangles. So if I wanted to find the approximation using 4 rectangles, I would substitute 4n for n, and that will give me an approximation. So let's see what we get if we substitute 4n for n. So if you use 4 rectangles, plug 4 in for n, and you should get the approximation, the right endpoint approximation using 4 rectangles to be what? I hope you got 25 over 4. Yeah. All right, now if you wanted to use 6 right endpoint rectangles, take n and plug 6 in for it. What if you wanted to find the exact area? Okay, if you wanted to find the exact area under that curve, think about what I said at the beginning of the video. The idea is if I have n rectangles, if I increase n to infinity or as large as you could possibly think, each of those subintervals or the widths of each of those rectangles will start being so small that they'll be stacked on top of each other. Add those areas up and you get the exact area. So what does that look like using a limit? That looks like this. So here's the notation as the limit as n approaches infinity of the change in x, 2 over n, times the function value at those right endpoints, which we already classified to be the function value at 2 over n times I. Okay, we already know what that summation expands to explicitly. That expands to this explicitly. Okay, and you can combine your common terms if you'd like, but the idea is now, if you're going to let n approach infinity, those expressions that have an n in the denominator, as n gets larger, they approach 0, so that basically goes away. This goes away, and now we just have, to calculate this limit, we have 10 minus 8 thirds, which turns out to be 22/3. That would be the exact area under the curve. F of x is equal to 5 minus x squared from 0 to 2. That is the foundation of knowing how to calculate the area under a curve using that limit and summation notation. Okay, so I hope this video helped. Please let me know if it did. Please let me know if it didn't. I will make another video talking about the integration techniques very, very soon. So look for that, and I'll see you in the next.